So we know that signals can be represented both in time domain or equivalently in the frequency domain through what are called as phasor representation. That is, if you have a signal v of t, then it can be equivalently represented as a phasor, complex phasor, as v of omega. And turns out that this is a complex phasor, and turns out that by this representation the operators like differentiation and integration, for example dv over dt, this becomes simply algebraic operations when it comes to phasors. And similarly, if you have integration, let's say minus infinity to t v of t dt, this is going to be equivalent to 1 over j omega v of omega. We know that differentiation, the inverse operation of that is integration. Similarly, in the phasor form, multiplying by j omega, the inverse of it is 1 over j omega. These becomes the features that we can get out of representing the time domain signal in terms of the complex phasor. Now, to prove this, it's pretty straightforward. We can see that this v of t can be recovered from the phasor by taking the real part of the phasor times the e power j omega t, the time dependence convention that we follow, e power j omega t. Remember, v of omega is going to be independent of time, and the time dependence is purely captured by this e power j omega t term. So the dv over dt is simply then going to be d by dt of the real part of the whole term here, and that, since v of omega is independent of time, this is independent of time, and we are taking the real part of this whole expression, this is equivalent to taking the real part of v of omega d by dt of e power j omega t. And differentiation of e power at, we know that is e power at. So based on that fact, this whole term becomes taking the real part of j omega v of omega e power j omega t. So this operator of d by dt that we have here, so this operator of d by dt that we have here has reduced to this j omega times v of omega e power j omega t in the phasor form. Similarly, we can show that the integration is 1 over j omega. Now, using this fact, we can find what is the so-called impedance of any element, whether circuital element. The ones that we know are resistors, a resistor, maybe an inductor, and a capacitor, the three common circuit elements that we know. And a complex circuit load passive load can be consisting of a resistor in some form, a capacitance in some form, or an inductor in some form. And we would want to know the relationship of the voltage at the terminals of that circuit to the current that goes into that circuit. To be able to do that, this phasor representation makes things a lot easier, so that we can define the ratio of voltages to currents in this complex representation as what is called as impedance. And that impedance is a complex number, Since v and I are phasors, this impedance in general is a complex number. It has both the real part and an imaginary part. The real part, we call it as the resistance, and the imaginary part is what we call as the reactance. And 1 over the inverse of the impedance, typically denoted by y, is what is called as the admittance. Again, it's a complex number having both a real part and an imaginary part. The real part is called as the conductance, and the imaginary part is called as the susceptance. So for a simple resistor, turns out that the voltage in the time domain is simply the resistance times the current in the time domain. You have a simple relationship like this. And if you were to find the equivalent frequency domain representation, it's simply v of omega is going to be r times I of omega. So the ratio of v over I is going to be the ratio of V over I. In this case, the Z of omega is going to be simply purely R. It's purely having only the real part. The imaginary part, X, is 0 in this case of a resistor. Now for an inductor, the V of t is going to be L di over dt, whatever the current that flows through the inductor. D by dt of that current that flows through the inductor, V of t is going to be L di over dt. Now this in the phasor form, is in the complex frequency domain form, is going to be simply then based on the fact that we saw here. This is going to be simply j omega L I of omega. And when we take the ratio of the two, then j of z of omega is going to be simply j omega L. And we notice that when we compare to this form here for the impedance, we notice that the R, the real part, is 0, the resistance is 0, and the reactance is simply omega L. So the J is here, so X is the reactance, and that is going to be omega L, which is the reactance of a inductor. We call that, let's say, XL. Similarly, we can do the same thing for a capacitor, where the voltage across the terminals of the capacitor is going to be 1 over C minus infinity to T I of t dt, and due to the phasor representation that you see here, we can write the voltage in the frequency domain to be 1 over j omega c I of omega. So that means the impedance is going to be, the ratio of V over I is going to be 1 over j omega c. And comparing this with what we already have in the impedance definition here, we see that the resistance is 0, but the reactance is 1 over omega c. It's going to be negative 1 over omega c, because this is equivalent to minus j over omega c, because 1 over j is negative j for a complex number. So minus j over omega c. Comparing that, we notice that X, the reactance for the capacitor, is going to be minus 1 over omega c, which is what we call as XC. The reactance of a capacitor is negative, that of an inductor is a positive number, and for a resistor is 0.